Okay, so we're looking at an application of exponential functions, and we're looking at growth and decay. So even though things can double and triple, basically we don't use any other base except base e. So what we've got is all functions that decay, or all populations that grow or decay, can be modelled by this formula here. And it doesn't matter what the letter is. M is just what we're measuring, and we measure either an amount, like in a weight, or we can measure a number of things, like a bacteria size or the number of rabbits, which will be our example. So in terms of the formula, the subject, M, is the amount that remains after some time, T. Okay, so T is the time. MO, this is a subscript, it just means original, like the stuff we start with, the original amount. K is a constant. Okay, so that's either a number, it's usually a decimal number, but it's a number. Okay, so it's just a number, it's a constant. And T is in time, and the time is years or days or weeks or seconds or whatever, but it's a time component. Okay, so M is what we're measuring, MO is the original amount, K is a number, a constant, and T is time. Okay, when you're ready, come to the next slide. Okay, so when we've got growth, like all exponential functions, grow up, they go up and up and up like this. Okay, so that's growth, and decay is going the opposite way. What I've got is the horizontal axis is time, and so what I've got here is this section back here. Even though it exists as a function, it doesn't exist in practice because this is negative time, and we don't measure time going backwards. So basically what happens is the function just starts and just goes up like that. So we don't have that section there, and the same with this. That section doesn't exist on the curve because we don't have negative time, so the function just starts there and goes down. And that's what decay is. Okay? Now, when you have growth, the value of the constant is a positive, so you've got a positive number, and when you have decay, it's a negative number. Okay, copy that, and when you're ready, come across. Okay, so what we've got is 3 examples which will give you a good idea what we're doing. Okay, so I'm going to pause because I've left my calculator behind, so I'm just putting a pause. Okay, I'm back, you didn't even know, so I was gone. Okay, so what's the initial population of the rabbit? So the rabbit, that's the formula. Okay, so T is time, and time is measured in weeks. Okay, so we need to make sure that all the questions have weeks. If they don't, then we need to convert. So what's the initial population size? The initial population is 50. Okay, it's just that number out the front. So that's the initial population. How many rabbits will there be in 6 weeks? Well, that's the time. So M equals 50 times E to the 0.05 times 6. And you just chuck that on your calculator. 50, clear. 50 times... So 50 times... okay, equals, I'm calling my calculator 67.5, so we could say 67 or 68. Okay, depending on the rounding. So it's 67 or 68, probably 67 to be more accurate. Okay, and the last part of the question is how long before there are 1,000 rabbits to the nearest week? So that's how many we've got, so that's the subject, 1,000 equals 50 E, and the formula was 0.05 times T. So the first step is get rid of the 50 by dividing. Sorry. So the 1,000 over 50 equals E to the 0.05 times T. And the opposite of E is log, so that means that 0.05 T equals log ln of 1,000 over 50, which you can work out what that number is. And then to get rid of the 0.5, you just divide. Divided by 0.05. So, on your calculator, log, bracket, 1,000, divided by 50, close bracket, and then divide by 0.05. So it's going to take 59.9 weeks, which is about 60 weeks. Okay, so in 60 weeks we'll have 1,000 rabbits. Okay, so copy that down, and when you're ready, come across to the next slide. Okay, so there's a variation. Okay, we've still got a rabbit population, and we have to be told that the growth is exponential either in the wording of the question or in a formula. So the growth is modelled by, so that means it's exponential. Okay, exponential growth. So we have to be told it's exponential, or we have to be given the information some way. Okay, so after 2 weeks there's 50, after 15 weeks there's 120, but we've got to find the initial population. So in here, it's going to come down to simultaneous equations. So we've got 50 equals MOE. We don't know what K is, but I know that T is 2. And then the second one, after 15 weeks, 120 equals MOE. Same constant times 15 weeks. So we've got two unknowns. The two unknowns are MO and K. Okay, so we've got two unknowns and we've got two equations, so it's simultaneous. So in this particular case, we have to eliminate one of the letters, either M or K. In this particular case, it's easier to eliminate M, because if I divide the formulas of the equations, like if I'd call this one 1, call this one 2, if I go equation 2 divided by equation 1, the M's will cancel out. But I've got 120 over 50. I'll just write it all out. So I've got MOK times 15 over MOE to the K times 2. And as I said, they cancel out. And then so 120 over 50, that's a number, but I'll just leave it as that. And then what we've got here is bases with indices divided by base with indices, so it's going to be a subtraction. So I've got 15k minus 2k, like k times 15 is 15k, k times 2 is 2k, and when dividing, subtract. So I'll just cross off the 0, so it's 12 over 5 equals e to the 13k, and then to get rid of e we log, so that means that 13k equals log of 12 over 5, and then to get rid of the 13, just divide. Okay, so now we just put your calculator. So log bracket 12 divided by 5, close bracket, and then divide that answer by 13. And I got 0.0673. So you leave plenty of numbers. Now that's not the answer to the question. The question said what's the initial population, but now we can use the numbers. So we've got 50 equals MOE to the 0.673 times 2. So MO equals 50 divided by that number. Okay, and I'll just press pause and put on calculator. So I just did a little pause and I just put those numbers on my calculator and I got 43. Okay, so 43.7, so about 44. And it makes sense that the answer had to be less than 50 because in 2 weeks the population grew to 50, so that means we were expecting an answer to be less than 50, which we got. Okay, so in that particular case, you have to form equations. You always divide to get rid of MO, then you find the K value, and then you fill it in to get the M value, M0 value. Okay, copy that, and when you're ready, come across to the last one. Okay, so the last one is a radioactive question, and again, these are with the first two, you could have those with Decay where you're given the formula and find the amounts, but this one's a little bit interesting in that we've got the half-life. Okay, so we've got a Decay question, so M, not MO, but M equals MOE to the minus K times T, because we've got Decay. Now we've got years mentioned here, so that'll be what we're going to use for time. Now, we don't know what the original amount is, but we've got a half-life, so we just use these percentages. So we start at 100%, and half-life is half of it. Now it doesn't matter if we use, even if the amount was 60, the half-life is 30, but we just have to halve it. So the half-life is half of what you started with, e to the minus k, and time is 100. Okay, so that goes into that half, so that's 0.5. 100 divided by 50, I say, beg your pardon, that's 2. So 100 divided by 50 is 2 equals e to the minus k times 100. Then to get rid of e, we log. So log of 2 equals minus k times 100. And then k will equal log of 2, or minus log of 2 divided by 100. And we'll just do that to a few decimal places. So log of 2 divided by 100 equals 0.00693. Okay, so that's our constant with a minus sign. Actually, no, that's going to be a positive because the formula has a minus in front of it. So k is that positive number, but the formula has a minus. So that means that the formula is MOE to the minus 0.00693 times t. Okay, so that's our formula, and we're trying to find 10%. So, like for instance, 100 equals, no, see, I have to go back, and, because I've made a mistake, so I have to start the whole video again. No, I'll just fix it up from here. So, apologies, because that's wrong. I could start the video again, but I'm sorry, I'll just fix it up. Okay, so we've got the amount is 50. The amount we measure is 50, and we started with 100. So that means that that's 0.5. So I'm really sorry about that. So then it's log of 0.5. So k equals log of 0.5 with the minus sign over 100. So try that again. Log of 0.5 divided by 100. So it is still the same number, but I did make a mistake. So we'll fix it up. 0.00693. But that's okay. And so that number there, the amount is going to be, I'll change colours. The amount is 10%, and we start with 100. E to the minus 0.00693 times t. And then to get rid of e, we log. So 100 divided by 10 is 0.1 equals that again. Then take logs. And then divide. So t equals log of 0.1 over minus log of 0.1 over 0.00693. Okay, so log 0.1 divided by 0.00693 and get 332.3, and a frame of reference was years. So just see that it makes sense. So okay, we started with 100%. The half-life was 100 years, so 100, 200. Just make sure it makes sense. So it starts with 100. And we've got 80, 60, 40, 20. So after 100 years, it's going to be at 50%. And then after 200 years, it's going to be at 20. Half of that's 25. At 300 years, it's going to be at 12.5. And at 400 years, it'll be at 6.25. So 100%, 50%, 25%, 12.5%, 6.25. So halfway, somewhere in between there, will be 10%. So it makes sense that the answer is 300 and something years. Okay, so there'll be an exercise to do on Moodle, and that's it. Sorry about the mistake, and hopefully it won't have damaged you too badly.